Hello everyone, welcome to the refresher course in mathematics held at Ramanujan College, Rajat University. So this is my second talk. In this talk, I will be talking about introduction to mathematical models in epidemiology. In the first talk, I covered the introduction to mathematical models in ecology. Now, in this particular talk, I'll be talking about the basic mathematical models which are being used in epidemics in order to predict the future of the epidemics, how various parameters involved in the epidemic influence the growth of the epidemic, and whether our epidemic is highly spreadable or it can be controlled over a period of time. So all these things we'll be discussing in this particular talk. So to begin with, let us first define what do we actually understand by the term epidemiology. So epidemiology is basically a branch of science which discusses all the factors which determine the presence or absence of a certain disease in a population. And it is also, we can say, it is also a study of spread of the disease, how this particular disease is spreading in space and time in relation to various factors which might affect the spread of that particular disease. So why it is important to study epidemiology, or why at all we talk about epidemiology, is the reason being that there are certain disease in a population where there are various factors that can actually increase the rate of the disease or decrease the rate of the spread of the disease. So epidemiology actually helps us to understand what will be the future of that particular disease, or what will be the dynamics of that disease, whether it is going to spread very fast, or there are certain factors in the population which, if controlled, can actually control the epidemic. So all these things actually, in order to study all these things, we have to first understand the science of epidemiology. So that's why it is very important to understand the mathematical epidemiology. So mathematics has a very important role to play here because recently, actually since a long time, there are several models, mathematical models, which have been used very widely in epidemiology to understand the future prospect of any epidemic. So if anyone interested to get more details of mathematical epidemiology, other than what I'll be covering in this talk, then one can see these two books, which are very popular and very good books. First one is by Hesterbeek and O. Diekman, and the second one is by Maya Marcheva. So yeah, so this is for the details anyone interested in the mathematical epidemiology. So let us first see what this epidemiology, how it evolved in history. And for this, the first name that comes into mind is Hippocrates, who was actually a physician, and he was actually the first epidemiologist. So he wrote 3 books entitled Epidemic 1, Epidemic 3, and on airs, waters, and places. Attempted to describe. So he attempted to describe diseases from a rational perspective. So before him, there was more mythological and superstitious beliefs about diseases. So he was the first one who actually gave a scientific explanation to the disease, and he was called as the first epidemiologist. Later, the detailed data study on the disease was done by John Grant in 1620 to 1674. So in his book, Natural and Political Observations Made Upon the Bills of Mortality, he has compiled a very large number of data in that decade as well. So the Bills of Mortality, the book that he has written, it has a weekly records of numbers and causes of death in London. He basically analyzed various factors that was causing death, and he gave a method of estimating the comparative risk of dying from various diseases. Then the first mathematical model was for understanding for epidemiology. It was given by Daniel Bernoulli, and the first mathematical model that he proposed, it was of smallpox. Now, before understanding the basic mathematical models in epidemiology, first of all, let us have a little bit detail of the background. So, we study the epidemic in a closed population. Most of the mathematical models that we will be studying is studied in a closed population. So, in general, the population of hosts, they show demographic turnover. What does that mean by demographic turnover? So it means the old individuals disappear by death, new individuals appear by birth, and also individuals increasing or decreasing due to the process of migration. So all these things come into this demographic turnover. So any demographic process, it has its own characteristic time scale. For humans, it is of order 1 to 10 years. So the time scale for any disease, infectious disease, is usually very short. For example, for influenza, this is in the order of weeks. So, in such cases, we actually choose to ignore the demographic turnover. This means we ignore the emigration and immigration, any change in the population due to that happening in the model while modeling the any epidemic using our mathematical model. So in that case, what do we call that particular population to be closed? So we consider a closed population, and then we ignore the immigration and immigration. So we consider a closed population, and then thereafter we study the disease in that particular population. Now let us suppose we have a closed population, and we assume that a certain disease-causing organism or pathogen has encroached that particular population, has entered into that particular closed population. All right. Now, the questions that may come into our mind is, first, can this cause an epidemic? So, when one disease-causing organism has been introduced in that particular closed population, can this break into an epidemic, or will it just remain as any ordinary disease? Second question that we can ask is, if it can happen, if it can break into an epidemic, then with what rate does the number of infected hosts increases during the rise of the epidemic? The third question that can come in our mind is, what proportion of the population will ultimately have experienced infection? So these questions are very relevant and very important to address when we are talking about introduction of a pathogen in a closed population. So what are the prospects that can happen? What is the future of the epidemic, whether it is an epidemic or it's not an epidemic? So in order to answer these questions, we'll get in more detail of the basic mathematical models for any epidemic. And the basic methodology that we follow that in a certain closed population are the following. So first of all, we have to formulate certain assumptions for the transmission. For many disease, transmission takes place either when the two hosts contact each other by several means, or it also depends upon their interaction. So sometimes the contact can be a little bit vague. So there are 3-step protocols that we follow in order to study an epidemic in a closed population. First is, we first model the contact process. So how the hosts are contacting. That is the first step in the modeling. Second is to model the mixing of susceptibles and infected population. That is to specify what fraction of contacts of an infected population are there with the susceptible population, given the population composition in terms of susceptible and infected. So this means after modeling the contact process, the second step is we check how the susceptible and infected populations are mixed together, how they are interacting with each other, what laws are they following. That is your second step. Third is to specify the probability of contact between the infected and the susceptibles, which can actually lead to the transmission of the disease. So this is another thing that we must keep into mind, is the probability of contact. At what rate is the contact possible between the infected and the susceptible individuals. Now, so this is the 3-step protocol that we follow for modeling any epidemic. Now, in a closed population in particular. So then we come to various mathematical models, which are also known as compartmental models. So what is a compartmental model? A compartmental model is a type of mathematical model described by a set of mathematical equations which explains how individuals in different compartments interact within a population. So by different compartments, we actually mean the different groups of individuals or different set of individuals of one type. For example, when I talk about susceptible or exposed compartment, so here exposed compartment, I mean it consists of all those individuals who are exposed to certain disease. So that will include one particular compartment. Similarly, infected compartment, recovered compartment, and so on. Now, the compartments of the model can either flow between each other or they can interact. So by saying that they can flow between each other, when I say that the compartments of the model, they can flow between another compartment, I mean that for instance, live individuals can flow to a dead compartment with a certain rate. So that by that I mean it's a flow between one compartment to another compartment, or they can interact. So interaction also, for example, any interaction between the susceptible and exposed, or exposed and infected, this interaction, if we incorporate in the model, we call it as just a simple interaction between the individuals of two compartments. Now, there are various compartmental models in epidemiology which have been since a long time they are used in order to model different epidemics. So here we will start with the basic SI model. So we'll try to understand some of the basic SI, SEIR and several other compartmental models which exist in the literature. Okay, now the rate of flow between the compartments and the interaction rate between the compartments, they are known as parameters of the mathematical models. Just now I explained in the previous slide that that for any two compartments in a compartmental model, either there can be flow or there can be interaction. And if we consider both of them, any of them actually, so then they are known as parameters of the model. Now, for example, here we can see beta. Beta is the rate of interaction between the susceptible and infected individuals. So basically, susceptible is one compartment, infected is another compartment, and beta is the rate at which the susceptible individuals interact with infected individuals, and the susceptible gets converted to the infected population. Now, during the formulation of these models, the population under study is divided into different mutually exclusive classes. So this is something that is an important point, that all these classes, they are mutually exclusive in nature. Now there are also, as I mentioned, some standard mathematical models. One of the standard mathematical model is SI model. Then this is SI model with the death rate incorporated here, delta I. So here there is a conversion of S to I at the rate of beta, and here sorry, it was not death rate. So here I gets converted to S again. This means once the population of the infected population is recovered, it goes back to the susceptible population again at the rate of delta. Now, the next standard model is SIR model, also known as susceptible, infected, recovered model. So it was proposed by Carmack-McKendrick, and it is one of the simplest yet very efficient epidemic model studied in epidemiology, mathematical epidemiology. So in order to understand what is this SIR model, we'll have to first define the various compartments in this SIR model. So there are three compartments in this SIR model: S, I and R. So by S we mean susceptible in population, I is the infected compartment, and R is the compartment consisting of removed population. So susceptible population, by the term susceptible we mean it comprises of those individuals which can contract the infection and can become infected. The infected compartment, on the other hand, includes those individuals which are capable of transmitting the disease to the susceptible population. And the removed population R is a compartment which includes those individuals which have contracted the disease and it has either died or became permanently immune once recovered or have been isolated. So that is how this delta I was also coming here in here I. So it has either recovered as it has gone back to the susceptible class. Now assumptions which are involved in the formulation of an SIR model are the following. So first assumption is that the total population remains constant. So as we discussed earlier as well, this population is considered to be closed. So for the SIR model, the population is closed. Now the second is the number of susceptible individuals who contracted infection from an infected individual per unit of time at a given time t. It is directly proportional to the total number of susceptible individuals with the proportional coefficient beta, which is also known as transmission coefficient. Now the individuals from the infected compartment are moved to recovered compartment at the rate proportional to the number of infected individuals, that is gamma into I. Now here gamma is your recovery rate coefficient, and it is also assumed that the recovered individuals gain permanent immunity. So with these assumptions, this is the basic SIR model without vital dynamics. So here by the term vital dynamics I mean that we are not considering the death and the birth in the population, given population. So based on the above assumptions, so the model that takes a mathematical form is given here. So here ds dt is equal to minus beta si. So this means the susceptible population gets into the infected compartment by at the rate of beta. So that's why it is coming here as minus beta si. Now this is infected compartment and this is di dt, that is beta si minus gamma m. So here there is a growth of infected population due to the interaction with susceptible populations, and minus gamma I. So here this at the rate of gamma, the individuals in the infected class gets recovered and they go to the recovered class. So recovered class growth rate is gamma times I. Now there are some modified form of SIR models. So first one is SIR's model. So this is, here we can see it is it's same as SIR model. Other than that, there is just one extra arrow here that tells that individuals from the recovered class goes to the susceptible class, and the rate at which it goes is delta. So basically they again become susceptible to the disease after recovery. And here the another modified form of SIR model is SIRI model, where we can see there is a movement from the recovered class to infected class again at the rate of delta. And when we consider the SIR model with the vital dynamics, then we consider their death rate, the death rate of each of the compartment, that is shown here as minus mu s, mu I and mu r, which is natural death rate. Now another model is in the literature that is being studied is SEIR model. So what is so here we actually introduce a new class of a new compartment of the disease. So here this is exposed population, or E. So the exposed compartment consists of population which is exposed to the occurrence of vital event. For example, the total population in the case of death, etc. So this, by introducing exposed class in the mathematical model SIR, we get a new type of mathematical model to study any epidemic, that is SEIR model. So this SEIR model, even this can be used in those types of diseases where the population is exposed to the disease or the pathogen, and it's still they are not showing the symptoms. So one of the best examples can be the coronavirus that we see these days. So coronavirus is there. The population is exposed to the pathogen, although it doesn't show any symptom, and they can be put into the exposed class. Now, to include the so during the formulation of the SIR mathematical model, it is assumed that the susceptible individuals immediately become infectious once contracted infection. However, in the case of SEIR model, it is used in those types of disease where there is a small period where the exposed population, the susceptible population, although exposed to the infection, do not show the symptoms. So the mathematical form of this SEIR model can be presented like this. So here ds dt is equal to minus beta si, de dt is beta I minus sigma e, and di dt is sigma e minus gamma I, and then dr dt is gamma I. So here in this exposed class, there is increase in the population from the infected class, that is beta I, and minus sigma e. So some of the population from the exposed class is going out from here and joining the infected class. So the flow diagram of SEIR model can be shown something like this here, and we can again assume there are situations or there are diseases where the recovered class, the individuals from recovered class can again become susceptible, and this is one of the best ways to understand such a process is currently the COVID is going on. So here once they are recovered, an individual recovered from COVID can again become susceptible. So here this is your modified SEIRS model, and it can model diseases like COVID and many other similar diseases or epidemic. Now, before getting into details of any mathematical model of epidemiology, we need to define a few of the important terminologies that are being used in studying any epidemiological model. So first one is the contact rate. So the total number of individuals contacted by an infectious individual per unit of time is termed as contact rate of the infection. And in general, all contacts with infectious individuals do not result in an infection. So then comes your adequate contact rate. What is the adequate contact rate? Suppose that the probability of infections by each contact is beta naught, and UN is the contact rate. So here n represents the population size under consideration. Then the function defined as the product beta naught UN. This gives the adequate contact rate of the epidemic, and in particular it describes the infection strength of the infected individuals. So that is another term. Then during the formulation of the compartmental epidemic model, the population can be divided into mutually exclusive compartments as mentioned earlier as well. So among all these compartments, diseases are transmitted only to individuals belonging to susceptible compartment when they come in contact with the individuals of infected compartment. So in that case, there comes this infection rate. So what is infection rate? If the total population is n, then the fraction of the susceptibles in the population is S by n. So from this, we can obtain the mean adequate contact rate of an infected individual to a susceptible. as beta naught un s upon n. So this rate is termed as infection rate. So what is infection rate? It is nothing but it is the mean of the adequate contact rate that we obtain. Then next one is the incidence. So how can you define incidence? So the total new infected individuals of in the infected compartment per unit of time is known as incidence of the disease, and mathematically we can write it as beta naught u, which is function of n times si by n. Now there are two types of incidences frequently used during the disease modeling. One is bilinear incidence and the other one is standard incidence. So what is bilinear incidence? So if the contact rate is proportional to the total population size, then the incidence is beta si, and this type of incidence is called bilinear incidence or simple mass action incidence. Now what is the other type of incidence is known as standard incidence. So how can I define standard incidence? So if the contact rate is a constant c, so in this case the incidence becomes beta si upon n, where beta is equal to beta naught c. So this type of incidence is known as standard incidence. So the next terminology that we come across in mathematical epidemiology is average lifespan. So what do we understand by average lifespan? So suppose we consider a small population size population of size n, and we will suppose that individuals in this population n have an age a. After that, mu is the proportion of the individuals who die out in that population per unit of time. So this mu is known as natural death rate coefficient. Now if we see the growth rate in this population, so with respect to their time t, which is a here, is age. So d and dA is can be written as minus mu n. So from here we get, solving we get n is equal to n naught e power minus mu a. That is e power minus mu a becomes n upon n naught. Now the probability of death of the population for the age interval 0 to a is 1 minus e power minus mu a. Now if we take the probability density function for this population, so it comes out to be of the form something like this. So the mathematical expectation of tau can be given by integration of this a mu e power minus mu a from 0 to infinity, and when we simplify we get 1 upon mu. So this is your average lifespan. So using the mean of mathematical expectation, we deduce that 1 upon mu is the average death age of the population, which is also known as average lifespan. Now the next is waiting time, so and average infection age. So the inverse of the probability of transmission of infection is termed as average infection age, and it is also known as waiting time. Next, one of the very important term that is used in mathematical epidemiology is basic reproduction number. So what do we understand by basic reproduction number? So basic reproduction number can be defined as average number of secondary infections that an infected individual can produce during his or her entire period of infection. So this means, suppose this blue person is an infected person. When he is introduced to any population of susceptibles, the number of infections that he can cause during his entire infectious period, that is your reproduction number for that particular disease. So in order to better understand it, we can see this example. So here this is an infected person in red, and he can actually infect 2 people in the population, and further each of these infected person can infect 2 more person at a time. So this gives rise to R value of R naught to be equal to 2. Now depending upon the value of R naught, it can determine whether a given disease will turn into an epidemic or it will subside. So for example, here I said that R naught is equal to 2. This means we can clearly see that from one person, this infected person, we are having so many infected persons. So whenever your R naught it is greater than 1, this means the pathogen is able to invade the susceptible population, and that particular pathogen can turn the disease into a epidemic. Whereas if the value of basic reproduction number R naught is less than 1, then we can say that the infection might not turn into an epidemic, and we can also predict that the infection will die out of the population after a certain period of time. Now, there are several techniques that we use to calculate the reproduction number. One of the famous methods to calculate the reproduction number is known as next generation method or next generation technique. So there are some references, important references, which can be used to understand this particular method in more detail. So here, suppose that so I'll explain this method in very brief here. So suppose a given disease transmission model with non-negative initial conditions can be written as given in equation number 1. So here xi dot is equal to f of xi, that is equal to capital Fix minus Vix. Now this capital Fix, this represents the rate of appearance of new infections in any compartment I, where I is equal to 1 to n. So this is the rate of appearance of new infections. Now what is this Vi? Vi is the difference between the rate of transfer of individuals out of the compartment, termed as Vi minus, and minus Vi plus, which is the rate of transfer of individuals into the compartment I. Now, it is also assumed that these functions which we have used in equation 1, they are at least twice continuously differentiable in each variable. Now, if those functions involved in equation 1, they satisfy these 5 axioms, then we proceed to this technique further, and we calculate the derivative of f and v. So derivative of f and v, sorry, this should be v. So derivative of f and v, it gives us f0, 0, 0, and this is v0, j3, j4. So j3, j4 are the matrices associated with the transition term of the model. So here f is basically this term f and this term v are the important terms which we'll be using in this technique. So we'll calculate the value of f, which is non-negative M matrix, and v, which is non-singular M matrix. And once we calculate f and v, then we get the next generation matrix as a product of f and inverse of this matrix v, that is fv inverse. Now the entries of fv inverse is the expected number of new infections in any compartment I, produced by the infected individuals originally introduced into compartment K. So once we obtain this product fv inverse, then we obtain its spectral radius, and that will give us the next generation matrix. So that will give us the value of the reproduction number R naught. So spectral radius of fv inverse is giving us R naught. Now we'll see an example here to understand this next generation technique in brief. So here this is an SEIR model. Then in this SEIR model, we obtain first the disease-free equivalent point given by here as E naught equal to 1, 0, 0, 0. So for this disease-free equivalent point, we obtain the transmission matrix F and the transition matrix V. So these two matrices, F is known as the transition matrix and V is your transmission matrix. So this transmission matrix F and transition matrix V are calculated here from this equation. So basically we calculate F and V from these two equations, d dt and di dt, because these are the only two infection states of the model and not S and R. So we use these two equations. From here we obtain the value of f and v. So the f comes out to be b naught b. So basically this b naught is coming from here, b naught se, and this beta is coming from here, beta si. And here then from 0, 0 is coming from this equation. So there is no interaction between I and E. There is no term of interaction between I and E in this equation, and I and S in this equation. That's why it's coming out to be 0, 0. Now similarly here this V is, we calculate from these two equations E and I. So V, alpha plus alpha 1 plus mu is coming from here, alpha plus alpha 1 plus mu. And similarly the other terms we are getting from E and I in the equations of d dt and di dt. So once we get the value of f and v, then we calculate fv inverse, and from here the r0 can be obtained using, as I mentioned here, as a spectral radius of fv inverse rho fv inverse, which for this particular example we are obtaining something like this. So these are we discussed some of the basic mathematical models in literature and the terminologies that are being used to study any epidemiological model. Now we will consider an example that is we have worked upon, our research group has worked upon. So this is a compartmental model which we used for finding out the future course of COVID-19 in Italy. So I won't be going into details of this particular problem, rather I'll just stick to the modeling part and just a few results to understand how do we interpret the results in a model in epidemiology. So here we have considered an SEIR model, a standard SEIR model. And since the reason why we have considered here SEIR model is that there is a latency period for this COVID-19 disease that ranges up to 14 days. This means up to 14 days the individual is exposed to the pathogen although does not show any symptoms. So we can categorize such individuals into the class of exposed. So as we defined earlier, exposed class is nothing but it is collection of those individuals which already got infected but they're not showing any symptom of the disease. And then with this assumption we define our mathematical model something like this. So this is our deterministic model. So here we can see the movement of the individuals from one compartment to another, which can be seen from this flow chart. So here this SEIR model, here we can see that this individual from the susceptible class move to the exposed class at the rate of beta I plus beta naught E upon n, and similarly from the exposed class the individuals are moving to recovered class at the rate alpha 1 and so on. So now this is a mathematical model, a simple SEIR model which is being modified for a particular epidemic of COVID-19, and that too in a particular domain a special domain that we considered as Italy. So we studied this mathematical model, and we first for that purpose, since this is a model of current scenario which we are going through, so what to make this particular mathematical model more realistic, what we have done is that we have estimated each of the parameters involved in the mathematical model. So the estimated value is presented here for each of the parameters, and with that estimated parameter what one can do is that one can see the future course of that particular pandemic. So we first did the data fitting of that particular mathematical model, and we used the real data for the active cases in Italy for a certain period of March to May, and we saw that our data, our mathematical model that we formulated here in equation number 4, that fitted very accurately to the real data. So here the dotted red dots that we see is the official data taken from the WHO site, and the blue line is the simulated data. So basically this is showing our model simulation from the mathematical model. So we see that our data actually fitted, our mathematical model actually fitted the data very accurately, and then one can use such mathematical model for finding out the future course of that particular pandemic. So we try to predict this till November 2020. So this is a study which was done last year in the month of March. So it's an old study, but one can use it very clearly to predict the future course of the pandemic. Similarly, we can obtain the basic reproduction number to get an estimate of the future course of the pandemic. So the method explained earlier, that is next generation technique, can be used. So for that we obtain the transmission matrix and the transition matrix FMV, and then we use those two matrices. We obtain the product FV inverse. From there we obtain the spectral radius, and that is how we have obtained the value of R0 for this particular mathematical model. So once we get the expression for R0, then it is quite easy to obtain its accurate exact value using the real data available. So the value of R0 that we obtained for in the case of Italy was 2.0683, which was pretty high and was showing that which is greater than 1, and it shows it's a case of epidemic. Then we also calculated the value of this R0 for the small provinces of Italy. So we considered 4 provinces here, and this is Lombardia, Veneto, Emilia Romagna and Piemont. And we calculated the basic reproduction number for each of these states, and we saw that Lombardia has the highest value of 2.1382, and real data also tells the same thing, that the scenario of this epidemic in Lombardia was the worst among all these 4 states. Further, one can study the effect of various parameters on the change in the reproduction number, which actually tells us how good or bad that particular pandemic is. So here, once you change the value of theta and alpha, then we can see that R0 is increasing over time. So that tells, and also the change in the value of theta as it increases, the steep is quite high. So this actually shows that theta is much more sensitive parameter in this disease, and it can actually has a significant role to play in the control of the disease. Similarly, other parameters can be simultaneously plotted, and its effect on the R0 can be seen. For example, alpha and alpha 2 here, alpha, beta, beta naught and beta. We plotted these parameters and we saw its effect on the R0. And we can similarly we can interpret it that as your beta changes. So wherever this parameter changes and there is a steep rise in the value of R0, or if there is there's not much significant change in the value of R0 for another parameter, so we can comparatively say that beta is a much more significant factor, and it can influence the disease in a relatively significant manner. Now we also calculate the endemic equilibrium point for any disease, because understanding the nature of the endemic equilibrium point has a significant contribution in understanding a given pandemic. So what is an endemic equilibrium point? It is the state when the disease cannot be completely eradicated, but it still remains in the population. That is your endemic equilibrium state. And for any disease to persist in the population, the exposed class and the infected class must not be zero at the equilibrium state. So this means E and I, it has to be there. It should be non-zero in order for any disease to exist, or in order to determine the endemic state. So we used our equations. We equated the steady state to Z. We obtained the steady state equation from our mathematical model, and we solved it, and we obtained the value of S star, E star, I star, R star, which actually eventually gave us the value of the endemic equilibrium point E star. So here E star is given by this, R star is this, which is in form of I star. Then this is your S star and I star. So there exists a unique endemic equilibrium point for our proposed model system as obtained from here. Now once we obtain the endemic equilibrium point, we check the stability of the endemic equilibrium point. So we also the disease-free equivalent point that we have obtained, we also check the stability of the disease-free equivalent point as well. So the disease-free equivalent point of the proposed model system is locally asymptotically stable only when R naught is less than equal to 1. Whenever this R naught is greater than 1, then the disease-free equivalent point becomes unstable. Now, if R naught is less than or equal to 1, then the disease-free equivalent point in this case is also globally asymptotically stable. Another theorem that we obtained here in our study was when R naught is greater than 1, then what happens to the stability of the endemic equivalent point. So we saw that the endemic equivalent point E star is locally asymptotically stable when R naught is greater than 1, and these two inequalities are being satisfied. Now another aspect in any epidemic study of any epidemic mathematically is understanding if there is any backward bifurcation in the system or not. So why this study of backward bifurcation is important is, in case there is any backward bifurcation in the mathematical model, then the control of the epidemic becomes very, very difficult, and making R naught less than 1 is not a sufficient condition in that case in order to control the disease. So we investigated the backward bifurcation in the mathematical model, and we saw that there existed backward bifurcation in the system whenever this beta naught is greater than alpha 1 plus theta plus 2 mu. So this actually points us to the fact that the condition of this COVID-19 was have been pretty bad, and its control has been very difficult. One of the reasons we can point out to is the existence of backward bifurcation in the system. Now another mathematical model which we can comparative mathematical model which we can understand in this mathematical epidemiology is one which we have studied. It is to study the impact of environmental pollution on the spread of waterborne diseases. So here we consider the total population to be n at any time t, and we divide this population n into susceptible population which is not under the effect of pollution. Then another one is susceptible population which is under the effect of pollution, which is x2, and the infected population y. And then we further consider B to be the pathogen population which is spreading the disease. So with these four compartments, we define our mathematical model something like this. So this is dx1 dt, dx2 dt, dy dt, and db dt. The flow of the individuals in this mathematical model can be shown here as represented in this diagram. So this is how we can actually consider an compartmental model to understand any waterborne disease and to understand various factors. For example, here we have assumed the environmental pollution as one of the factors and its role in the spread of the waterborne disease. Another mathematical model that we have studied in our group is effect of pollution in the cholera modeling. In particular, we have considered one particular waterborne disease, that is cholera, and we have tried to see what is the effect of pollution in the cholera model, in the disease, waterborne disease cholera in particular. So for this purpose, we formulate a deterministic compartmental model, and here we divide our total population n into mutually exclusive compartments, again x1, which is the susceptible population which is not under the effect of pollution, and x2, which is the susceptible population which is under the impact of pollution, and the infected population y. And b is the density of the pathogen population that we have considered. Now here we have considered both the modes, that is human to human and environment to human transmission during the model formulation. So here we have x1, x2, y and b. So here also we have only 4 compartments, but that mode of transmission is much more complex than it was considered in this particular mathematical model, where we only considered the mode of transmission to be from water to human and not the human to human interaction. So the flow of the different individuals from the different compartments can be shown from this transition diagram as presented here. And so what we can see is that we can understand several factors which can actually control the epidemic with the help of mathematical epidemiology. And for that purpose, we use the mathematical models and the different techniques that are available to understand such compartmental models. And so what we do, we begin with the simplest model and we try to discover everything about it. We try to see what are the different environmental factors that actually affect that particular pandemic, and we try to incorporate it in the compartmental model. And so in the specific case of mathematical epidemiology, for decades, medical and public health officials have carefully conducted surveillance of infectious diseases, and we can use those data. It can be used to understand the transmission dynamics of any particular disease which we are interested in studying with the help of mathematical epidemiology. So that is all. Thank you.